Have you ever wondered why so many students lose easy marks in JUPEB chemistry practicals even when they know the theory? This practical is one of the most frequently tested redox titration in JUPEB, IJMB, A-level and first year university chemistry practical examination. In this video lesson, I will show you exactly how to prepare the solution, perform the titration correctly, identify the endpoints, also how to write balanced ionic equation, the common mistakes to avoid in practicals, and I will review the secrets to score maximum marks in your exam. So if you are preparing for JUPEB chemistry, this lesson could be the difference between an average score and an excellent grade. Let's get started. What is redox titration? Redox titration is a volumetric analysis based on electron transfer. Recall that I explained in this video lesson that oxidation is loss of electron and reduction is gain of electron. In this experiment, ion 2 ion lose electron and become ion 3 ion, and the process is called what? Oxidation. That's right. At the same time, permanganate ion gains electron and are reduced to manganese 2 ion, and the process is called what? That's right, reduction. Since oxidation and reduction processes take place in one single reaction, the experiment is called redox titration. Note that no indicator is required in this volumetric analysis because the potassium permanganate is a self-indicator. That is, it has intense purple color, therefore we do not need methyl orange or phenolphthalein indicator. Moving on, can we consider the question right here? You are provided with the following. In solution A, we have 9.8 gram of acidified solution of ammonium iron 2 sulfate in 250 cm cube of the solution. And the solution B is aqueous solution of potassium permanganate. It can be observed from this question that the solution of known concentration is ammonium iron 2 sulfate. Since the mass concentration is known, therefore it is regarded as the standard solution, while the KMnO₄ is of what? Unknown concentration. So we need to determine the concentration of potassium permanganate using the known concentration of ammonium iron 2 sulfate. Now, can we start the titration? Let's identify the solution given. We have the potassium permanganate, which is solution B, and we have the ammonium iron 2 sulfate, which is solution A. From the titration procedure, we are expected to introduce the potassium permanganate into the burette, and we have to pipette 25 cm cube of acidified ammonium iron 2 sulfate. I've introduced the potassium permanganate into the burette, so the next thing is to pipette the acidified ammonium iron 2 sulfate. Okay, so I'm going to pipette that now. Okay, so I have 25 ml, which is the same thing as 25 cm cube of the acidified ammonium iron 2 sulfate. So I'm going to introduce it into the conical flask. Do not force the last drop. So I have my ammonium iron 2 sulfate in the conical flask. Can we start the titration? So we release the potassium permanganate directly into the solution of the ammonium iron 2 sulfate. We observe the appearance and disappearance of pink color as potassium permanganate gets in contact with the ammonium iron 2 sulfate. So we continue to titrate until we see a permanent pink color change. Observe closely. We see appearance and disappearance. So we continue to swirl the conical flask as we release the potassium permanganate into the solution. Wow, this is what is expected of you in the exam. Here is the light pink color that indicates that the endpoint has been reached for this volumetric analysis. So can we record the titre value? We have 11.40. Moving on, can we conduct the second titration? So we carry out the same procedure for the second as well as the third titration. So the first thing we need to do is to pipette the ammonium iron 2 sulfate. So right here we have the 25 cm cube meniscus. So I'm going to introduce the solution into the conical flask. Remember, do not force the last drop, okay? So we have the solution of acidified ammonium iron 2 sulfate in conical flask. So the next thing is to titrate the potassium permanganate against the acidified ammonium iron 2 sulfate. The solution initially is colorless. Now, can we start to titrate the potassium permanganate against the solution in the conical flask until a permanent pink color is obtained, which indicates the endpoint? Let's get started. We ensure that solution is uniformly mixed. So we start to see the appearance and disappearance of pink color until an endpoint is reached, and the desired color that indicates the endpoint is a permanent pink color. Ensure that the solution of the potassium permanganate is not being released on the wall of the conical flask. Ensure that it is introduced directly into the solution of the ammonium iron 2 sulfate. Okay, so we'll continue to titrate. Can you see the appearance and disappearance of the pink color? Wow. Yes, we have our desired light pink color for this redox titration. So we can record the volume of the potassium permanganate used in the second titration. Now, can we check the endpoint for the second titration? We have 22.90. So we can discard the solution gotten in the second titration. Then we are going to rinse the conical flask. So after we've rinsed the conical flask, we are going to pipette solution A. That's 25 cm³ of solution A. So can we do that again for the third titration? So we release gently. Right here I have the accurate measurement, which is the 25 cm³ of the solution A. So I'm going to release this into the conical flask. This is the acidified ammonium iron 2 sulfate. Remember, do not force the last drop from the pipettes. Note that we can proceed with the third titration without refilling the potassium permanganate in the burette. So the volume that we have in the burette is sufficient enough for the third titration. So can we titrate the potassium permanganate against our solution A? So we can see the appearance and disappearance of the pink color. So the endpoint is reached when we have a permanent pink color change. So we start to add drop by drop. Wow. Can you see this? This is interesting. We have a permanent pink color change, which indicates the endpoints for this titration. So we've gotten the endpoint for the third titration. Can we take our reading from the burette? Now, can we take the burette reading? We have 34.50. So we can record the titre value for the third titration now. Can we state the burette reading on our table? For the first titration, we started from 0 meniscus. So we are going to have 0.00. Remember, we have to record to 2 decimal places. The final burette reading for the first titration is 11.40. Okay, so by the time we subtract 0.00 from 11.40, what do we have? 11.40. That's right. Okay, that's for the first titration. Now for the second titration, we continued the titration without refilling. So the initial is 11.40. So the final burette reading for the second titration is 22.90. Okay, by the time we subtract 11.40 from 22.90, what we have? That's right, we have 11.50. So the titre value for the second titration is 11.50. Make sense? Can we move on to the third titration? The initial reading is 22.90, okay, without refilling. And we got the final burette reading for the third titration as we have 34.50. By the time we subtract 22.90 from 34.50, what do we have? That's right, we have 11.60. Make sense? From the result gotten from the titration of potassium permanganate with ammonium iron 2 sulfate, we are to find the average titre value. How do we determine the average titer value? We are expected to pick the concordant value in our titration. So can we identify the concordant values? We have 11.40 is concordant with 11.50, and 11.50 is concordant with 11.60. Concordant values have a difference of 0.1 plus or minus 0.1. Okay, so the 11.40 is concordant with 11.50, and 11.50 is concordant with 11.60. So we just pick any two concordant values to determine our average titer value. Okay, so I'm going to pick the second titer value and the third titer value as my concordant values for this titration. So I have 11.50 plus 11.60 divided by 2. Okay, so this will give 23.10 divided by 2. 23.10 divided by 2. So we are going to have 11.55 cm3. Okay, we are expected to record to 2 decimal places. Make sense? Can we balance the ionic equation for this redox titration? We have the manganate ion plus the iron 2 ion plus hydrogen ion to give the manganese 2 plus iron 3 ion and water H₂SO. Okay, for the purpose of your exam, you can memorize this ionic equation for the redox titration between permanganate and the ion. It can be observed that 1 mole of permanganate ion reacted with 5 mole of iron 2 ion in this redox titration. So we've been able to balance the ionic equation for this titration. Can we move on to the next question? Which two processes occurred in the redox titration? We can observe that the iron 2 ion is converted to iron 3 ion. So what process is that? An increase in oxidation number reflects what? Oxidation process. So we're having what? Oxidation process. So Fe 2 plus going to Fe 3 plus is what? Oxidation. So we have oxidation right there. From this same ionic equation, in MnO₄ minus, manganese has the oxidation state of 7 right here, while in this ion the manganese is 2. So this is a decrease in oxidation number, which shows that reduction has taken place. So the second process is what? Reduction. So we have reduction process. So the two processes that occurred in this redox titration are oxidation and reduction processes. Make sense? Now can we consider the next question? The mass concentration of solution A. Solution A is the ammonium iron 2 sulphate. So we're given the mass contained in 250 cm3. So in order to get the mass concentration, we need to determine the mass contained in 1000 cm3. So we have 250 cm3 of solution A contains 9.8 gram. Then 1000 cm3 of solution A will contain X gram. Okay, so what is the value of X? We cross multiply 9.8 times 1000 divided by 250. We have 39.2 gram per dm3, which implies that 1000 cm3 contains 39.2 gram of ammonium iron 2 sulphate. Make sense? So we've been able to determine the mass concentration of solution A. So we've been able to answer the question number 1. Can we move on to question number 2? We have to determine the molar concentration of solution A. So we already know that molar concentration equals mass concentration divided by molar mass. Okay, so if we know the mass concentration and the molar mass of the compound we are dealing with, we can determine the molar concentration. We've determined the mass concentration of solution A, which is 39.2 grams. So we have 39 0.2 divided by what is the molar mass of this compound right here. By the time you calculate the molar mass of the compound, we are going to have 392, okay, gram per mole. So can we divide this? We have 0.1 mole per dm cube. Okay, so that is the molar concentration of solution A. Question number 3, we have to determine the number of mole of solution A. We can use this formula: N equals concentration times volume over 1000. Okay, so we already know the concentration in mole per dm cube, which is 0.1 mole per dm cube, and the volume of solution A pipetted during the titration is 25 cm cube. So we have 0.1 times 25 divided by 1000. So when you press your calculator, we are going to have 2.5 times 10 raised to power minus 3 mole of solution A. So this is the amount in mole of solution A contained in the 25 cm cube of solution pipetted. Since we've determined the number of mole of solution A, can we determine the number of mole of solution B in this titration? So let's make that Roman figure 4. Now from the ionic equation, we have 1 mole of manganese ion reacted with 5 mole of iron 2 ion. Okay, so we have 1:5. We have 5 mole of iron 2 ion requires 1 mole of manganese ion. Therefore, 2.5 times 10 raised to power minus 3 mole of iron 2 ion will react with, can we cross multiply? We have 2.5 times 10 raised to power minus 3 times 1 divided by 5. Okay, we are going to have 5 times 10 raised to power minus 4 mole of solution B. Makes sense? Moving on, can we determine the concentration of the manganese ion? We have the average titre value as 11.55 cm cube. So 11.55 cm cube of solution B contains this mole of manganese ion. So we have 5 times 10 raised to power minus 4 mole of manganese ion. Okay, now 1000 cm cube of solution B will contain, we cross multiply, we have 1000 times 5 times 10 raised to power minus 4 divided by 11.55. So what do we have? So we have 0.043 mole per dm cube of manganese ion. Make sense? We've been able to determine the molar concentration of manganese ion right here. Note these exam tips. If you are not good at balancing redox reaction, make sure you memorize the ionic equation. From the ionic equation, we have 1 mole of manganese ion reacting with 5 mole of iron 2 ion. Note that this mole ratio is extremely important during the calculations. If this lesson helped you understand redox titration with potassium permanganate, don't keep it to yourself. Give this video a like, subscribe to Organotope Chem Clinic, and turn on the notification bell so you never miss any of our chemistry practical lessons. Share this video lesson with your classmates and tell me in the comment section what chemistry practical topic would you like me to explain next. Remember, at Organotope Chem Clinic, we don't just prepare you for exams, we prepare you to excel. See you in the next lesson.